Okay, welcome all. Today we will discuss fundamental electromagnetic quantities which are basic requirement to study the electromagnetics. So as we already discussed that this electromagnetic is a combination of electric and the magnetic quantities. So we can partition it into the two basic parts, that is say electric quantity and magnetic quantity. Okay, so this electric quantity is electric field intensity, that is given by E, capital E, as it is a vector quantity. So we have this put a arrow above it. Okay, and the unit of this is volt per meter. We will see how this unit is volt per meter. Okay, the second quantity is this. The second quantity is electric flux density. Electric flux density, it is given by D and the units are coulomb per meter square. Okay, so two electric quantities which is used basically in the electromagnetics: electric field intensity E, unit is volt per meter; electric flux density D, coulomb per meter square. Okay, this is also called as a this electric flux density is also called as a electric displacement. Okay, it is also called as electric displacement. And these magnetic quantities, similarly we have the two magnetic quantities. The first one is magnetic flux density. Magnetic flux density. Okay, this is B. Now you need to remember this B is magnetic flux density. Many of the students are confused in this, that B is the electric field intensity like this E. Okay, but it is a magnetic flux density. So this should be clear in your mind. And the unit is Tesla. Unit is Tesla. And for this the second is magnetic field intensity. Magnetic field intensity. Okay, intensity. Magnetic field intensity, then the unit is H. Okay, sorry, it is given by H and the unit is ampere per meter. Okay, magnetic field intensity, it is given by H and the units are ampere per meter. So these are the four basic, or you can say four fundamental electromagnetic quantities: E, electric field intensity; D, electric flux or electric displacement; B, magnetic flux density; and H, magnetic field intensity. So in the complete this subject electromagnetic and or field and wave, we are going to modify these equations in every unit, in every topic, just going to modify these. Okay, electromagnetic is the behavior, to study the behavior of these four quantities, how they behave. Okay, so these are the fundamental electromagnetic quantities. Okay, and let us also discuss some another quantities which are not fundamental but basically used in the electromagnetic. So you should know what is the charge on an electron. Let's draw a line here. Okay, charge on an electron is 1.6 into 10 to the power minus 19 coulomb. Know that. Okay, and this, the moment of the charge will produce the current. So the rate of change of this charge dq by dt will give you the current. This is the current. This is the basic definition of the current. Rate of change of charge with respect to time is current. But in the electromagnetic, this current is a scalar quantity. I made this video on this, the scalar and this vector quantity, and you can see my previous videos for the basic knowledge of this electromagnetics, why we require electromagnetics, what is the use, where we use, okay, why we are studying it. So the link is in the description, so you can see that videos. Okay, let us continue now. Current is a scalar quantity. Okay, scalar quantities. What are the scalar quantities? The scalar quantity are those who have only amplitude but no direction. Okay, so in this electromagnetic, instead of this I, we use J. J is the current density, and J is equal to I upon A. Okay, J is equal to I upon A, current per unit area. Okay, this J is a vector quantity. This J is basically called as the current density. Okay, which is used in the electromagnetics. So instead of the I, we will use J. Okay, and we also have a relation between these two. One another parameter is this C. C is the velocity of the light. Okay, C is the, okay, let us write it. This is the current density, and this J is the current density, and this C is the velocity of light. You should know what is the velocity of light. What is it? What its value? This is approximated to 3 into 10 to the power 8 meter per second. This is approximately sign. Okay, so this is the value, approximate value. Now this D, E and D, and this B and H hold the relationship. Okay, this D is equal to epsilon naught E. I will define what is this epsilon, and B is equal to mu naught H. Okay, now let us define what is this epsilon naught and mu naught. Let us start with this mu naught. Okay, so mu naught, so mu naught and epsilon naught, this naught is used for the free space. The naught represent the free space. Okay, now we have already discussed this velocity of the light, and this mu naught is the permeability. This is the permeability. So this naught define here the free space. Okay, so let us see the value. The value is 4 pi into 10 to the power minus 7 Henry per meter. Now see the units. Units are Henry per meter. Those units as Henry per meter. This is of inductor. Henry is a inductor's unit. Okay, so you can say that this mu naught is a inductance of free space. As we have the mu naught here. Okay, inductance Henry per meter. Okay, so it is a distributed parameter. Henry per meter means inductance per unit length. Okay, I have discussed it in detail in my first video. Okay, who want to gain the basic knowledge of this electromagnetics, just see the first video. The link is in the description. that will give you why we study this electromagnetics. What is Henry per meter? Okay, why the unit is Henry per meter? Okay, because for the distributed parameters we use the this unit per meter length. Okay, so if you have doubt in this, you can see my first video. Okay, now come to this permeability. We have discussed mu naught. Let us come to this epsilon naught. What is this? This is the permittivity of the free space, because this is epsilon naught. Okay, if there is epsilon, then that would be a simple permittivity, but here epsilon naught is there, so it is a permittivity of the free space. And what's its value? Its value is 1 upon this epsilon naught is equal to 1 upon 36 pi into 10 power minus 9. And what are the units? Farad per meter. Now see the units are farad per meter. Okay, so this is the unit of farad, is the unit of the capacitance. Okay, so farad per meter, capacitance per meter. So what is epsilon naught now? It is a capacitance of free space, which is distributed throughout the length. Okay, so this free space is also having the inductance and capacitance, but it is distributed throughout the length. Okay, unlike this network theory, which is lumped. So if you want the differentiation between these two, lumped and the distributed parameters, you can see my previous video. Okay, again, now this epsilon naught and this mu naught also have the relation with the c, velocity of the light. How? The c is equal to 1 upon under root mu naught epsilon naught. You just put the values here. What is the value of mu? It is the 4 pi into 10 power minus 7. What is the value of this epsilon? 1 upon 36 pi into 10 power minus 9. You solve it. Okay, solve it. Cancel by the 9. Then if you solve it, you will get approximately 10 meter per second. Okay. So into 10 power 8 meter per second. So you have to remember this relation too. Okay, you have to remember all these relations. J is equal to I upon A. C is equal to what is the velocity of light, what is the current on a charge. Directly remember this. What is the relation between D and E, relation between B and H. Okay, what is the value of the mu naught, what is the value of epsilon naught. Okay, now it is clear in your mind what is the mu naught. It is the inductance of the free space. Okay, what is epsilon naught? It is the capacitance of the free space. Okay, now you can easily see it. Similarly, we have the resistance per unit length. We will discuss it in the coming videos. For the time being, just remember this. Okay, now let us see what are the static and the dynamic fields. Static and dynamic fields. Static and dynamic. Now if your this charge is in motion, okay, charge is moving with respect to time. Okay, so the field is called as the static field, because we have already discussed that we are studying the electromagnetics, and electromagnetic is the behavior of the charge in rest and in motion. Okay, we have discussed it, electromagnetics. Okay, so charge in motion, when charge is in rest, what is in motion, and then in both the condition it will behave differently. Okay, so just remember that when this charge is in rest. Okay, let us say this is a charge Q plus Q. Okay, it is not moving, then it will produce the electric field. When it is in the motion, then it will produce the electric field as well as the magnetic field. Okay, so what is the static fields? The static case is when your electric field is not changing with time. E field is not changing and magnetic field is not changing with time. That case is static case. No time variation. Okay, no time variation. Dynamic is when there is a time variation. Okay, we have already discussed that for the electric and the magnetic field we have more than one variables, time variable and the space variable x, y, z. Okay, we have used the simple Cartesian coordinate system. So if there is no time variation, so only this the space variation is left, so that field is called as the static field. Okay, x, y, z, only the space variation. Similarly for this magnetic field I am writing only for the electric field, so even also write. So that field is called as the static field. If there is a time variation, it would be a dynamic field, and both will behave differently. Okay, both will behave differently. Now how they will behave differently? Now we have already discussed what is the del. This is the space variation parameter, del operator. This is the del operator. Okay, what is its value? So del is equal to, I am writing here, del is equal to what? Ax curl by curl x plus ay curl by curl y plus az curl by curl z. This is del. So it will give you the space variation. Okay, and we have already discussed this gradient, divergence and the curl. Okay, so for this I have the separate video. You can see it, what is the gradient, divergence and the curl. The link is in the description. So if you want to study the static behavior of the electric and the magnetic field, so you have to write some equations. Let us say I want to study what would be the net flow of the electric field. So I will take the divergence of electric field. What will be the net flow? Because this is divergence, this is called as the divergence. Dot product of any vector quantity with the del operator is called as a divergence. Okay, simple, remember this. Okay, you can see my previous video, okay, for the divergence. So divergence will give you the net flow, del dot E. What is the net flow of the electric field? It will depends on the charge carriers. How much is the electric field? It will depends on the how much is the charge. Okay, larger the charges, larger will be the electric field. So you can say that this del dot E is directly proportional to what? Rho. Rho is the charge density. Okay, rho is the charge density. So in other words, you can directly write it like this: del dot E is equal to, just directly proportional is can be replaced by this epsilon naught. Okay, so this is the first equation. Net flow of electric field is equal to charge density divided by the epsilon naught. This is the first equation. Okay, similarly if you want to write the curl of this electric field, so if you want to write the curl, so curl, this C stand for curl. So this cross product with the del operator will give you the curl. Curl will give you the net circulation. So what is the net circulation of this electric field? In the static case, if it is not changing with time, it is 0. Del cross E is always 0 in the static case. Static means not changing with time, is always 0. It will not produce this circulation effect. Let us move it upward slightly. Okay, so it will not produce the, what is the curl? Curl signifies that the electric field will not produce the circulation effect. Now if this is the electric field, Okay, this is the electric field. If you put a charge here, static electric field, okay, I'm not talking about this dynamic. In this video I will talk about this static field. That field is not changing with time. Just not confused in that, because most of the student is confused in that, because in the static field del cross E is 0, means it is not changing with time, it is constant throughout the time. Okay, so this is the if you put a charge here, it will apply a straight force. It will move in that direction. Okay, in this direction. Okay, move the charge in the straight path, not provide the circulation motion. That's why del cross E is equal to 0, because the curl will give you the net circulation, and the circulation provided by the static electric field is always 0. Okay, so we have this is the second equation. First equation was the del dot E is equal to rho by epsilon naught. Okay, let's do it for the magnetic field. Now let us start with this divergence. The divergence of the magnetic field is del dot B. Okay, now del dot B will give you the net flow of the magnetic field, so it is always 0. Why? Because this magnetic field will always provide with a circular motion, whether it is static or dynamic. Okay, and this the circulation provided in the this work done in this circular motion is always 0, so the net flow is always 0. And you can say that you can define it with another method. Let us say this is a magnet having the south and the north pole. If you cut it in two parts, okay, so we will have a two equal magnets having the separate north and the south pole. Now again cut it in two parts, so we'll have a 4 magnets, and they will also have this north and south pole. Okay, so you the meaning here is you cannot separate the south and the north pole. So that's why these electric field lines are the closed lines, and that's why the work done by this magnetic field is 0, because you cannot separate this north and the south pole. And this, unlike this electric field, in the electric field we have the plus q charges and the minus q charges separately. Okay, you can separate these charges separately exist, but not in the case of this north and the south pole. Okay, these magnetic fields are the closed lines. Okay, you cannot separate the north and the south pole. That's why the net flow by this magnetic field is always 0, whether it is in the static field, whether it is in a dynamic field. And it will apply the net circulation. The source circulation is given by curl, net circulation. It is a net circulation by the magnetic field, and the circulation, larger the current, larger will be the circulation. So this net circulation is directly proportional to the current density. Okay, the circulation provided by this curl will give you the net circulation. The circulation, that is closed lines. So if you put a charge here in this magnetic field, it will try to rotate it in a circular motion, and circulation provided by the current, larger the current, larger will be the this circulation. So you can remove this proportionality constant, and you can write it as equal to J by mu naught. Okay, you can compare it with this equation. Okay, although it is a cross, it is a dot, but if you just don't look at on this, they are similar. Okay, so you can also write it as, you can take it as this mu here, and you can multiply it, and by using this formula, you can apply this formula or not. No, this is not. Here it is mu naught. Okay, rectify it. It is not in the divide, it is in the here in multiplication. Okay, so you can write here del, sorry for that, you can rectify it. This proportionality constant will be removed by this J in multiplication with mu naught. So you can write directly. Okay, so this is the third equation, and this is the fourth equation. Okay, so we have these four equations. Del dot E is equal to rho by epsilon. This is the first equation. Del cross E is equal to 0. This is the second. Del dot B is equal to 0, and del cross B is equal to mu naught J, fourth equation. And remember, these equations are in the static, electric and the magnetic fields. Static means the field is not changing with time. Just remember this, because if there is a variation of the time, then these equation will be changed. Okay, so these are the four basic equations which are you going to modify again and again for your requirement throughout this electromagnetics. So these are the basic equations which are you going to modify again and again. Okay, you should remember these equations. Okay, thank you for watching.